So our last activity for today is going to be 3.2.7 from the book, which is numbered 3.2.11 in your activity stream. And the idea of this problem is you have a linear transformation and you have its standard matrix. And we want to do two things. We want to compute t of 1, 2, 3. So what would it mean to transform the vector 1, 2, 3 by the linear transformation for whose standard matrix we have listed on the screen? And then in general, what would t of x, y, z look like for this particular linear transformation if this is its standard matrix? And if you'd like, it would also be nice to roll in the previous activity, which is 3.2.6 in the book, 3.2.9 in the activity stream, which does the opposite. It gives us a linear transformation and asks us to compute its standard matrix. So maybe let's start with this one, the 3.2.9 in your stream, 3.2.6 in the book, and then do the one after that as well, which is 3.2.11 in your stream. So we'll do both the back and the forth of going between a linear transformation and its standard matrix. So I'll set a 10-minute timer. That's going to run us a little bit past 7 o'clock, but if you can stick around, that'll be how we wrap things up for today. All right, so just to wrap up this activity, you were given a linear transformation and asked to determine its standard matrix. And the way we can do that is by transforming the standard basis vectors of the domain. Those standard basis vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1. And if we transform those, we get the vectors 1, 2, 0, minus 1, and 3, minus 4. And then the next step is where everybody screws this up the first few times that they do it. We take those vectors and we make them the columns of our standard matrix. And again, I would love to say that there is a deep mathematical reason for why they need to be the columns, but there isn't. There is just a preference on the part of mathematicians to be able to write matrix acting on vector with the matrix on the left and the vector on the right. And because that's the way that we want to write the action of a matrix on a vector, that's what forces the images of these standard basis vectors to need to be the columns of a matrix. And so that gives us this particular standard matrix, 1, 0, 3, 2, 1, minus 4. And so I think the thing that I would say to kind of keep this straight in your minds, even though it's going to be a little bit counterintuitive, is the following. That if t is a transformation from Rn to Rm, so if it takes me from an n-dimensional space into an m-dimensional space, then its standard matrix is going to have m rows and it's going to have n columns. Then its standard matrix has m rows and n columns. It's m by n. Right, so it takes the dimensions of the codomain and the domain and it reverses them in the dimensions of the matrix. So yeah, this is just sort of the slightly counterintuitive rule of thumb that's necessary for us to use if we want to use the column convention for our transformations, which we do because it's the convention that every linear algebra introductory textbook tends to use for this stuff. So nice work.